welcome to our talk. So over the course of the last 2 days, I don't think I've seen a single presentation that did not involve Kubernetes. So at least we'll fit the profile. To introduce us a bit, so Daniel and I'm Tim. We work for GoDataDriven. It's an IT consultancy company based in Amsterdam. We mainly focus on big data problems, and we kind of want to help companies use their data to make decisions. So we want to be data-driven, right? It's a small company, and currently we are situated there. So has anyone ever been there? This is Schiphol Airport, located in Amsterdam. So it's a nice airport. Here's some interesting facts. So it's about 500,000 airport movements per year, lots of passengers, and something that's quite interesting that we didn't know before we started working at Amsterdam Schiphol Airport is that it's actually part of the Royal Schiphol Group, and it's 100% shareholder in 3 airports in the Netherlands. Not only that, it holds approximately 1/5 of the stakes in Brisbane Airport, and much cooler, so who of you flew in on JFK? And so we also did that. So Terminal 4 of JFK is so the operating franchise holder is Royal Schiphol Group. So that's pretty cool. Schiphol itself is the 3rd busiest airport in Europe in terms of aircraft movement, and is the busiest airport in terms of passenger. So even though we're quite a small country, it's a really busy airport. So to get to our problem statement of the things we're trying to fix, which is flight delays, we have to get you into what a turnaround is. So I'd like to focus your attention on the purple part of the slide, which is the top half, which depicts everything the aircraft does from airspace to airport and back to airspace. So anything that happens between on blocks and pushback, which basically means you're at the gate and you leave the gate, that's what considered as a turnaround. And many things happen at a turnaround, right? So we have the passenger deboarding and boarding, there's the baggage loading and unloading, there's the catering truck, which needs to take care of a few things, there's refueling. So all these processes, everything that's happening here, basically the airport itself, Schiphol, doesn't really know much about what's happening here. So it knows a lot of things that's happening, everything before that, right? It knows everything that's happening in the airspace. It knows what's happening while taxiing. It knows a lot about departing. But everything that's happening in a turnaround is managed by the airlines itself. Which means if something happens here, the airport has no idea. So they have no idea which order these things take place in. They have no idea when these happen, how long they take. So if refueling happens 5 minutes before the flight leaves, you can imagine that this will lead to a delay. And the airport would like to know when this is going on. So, as you can see here, it's less predictable. They know something, and it's mainly because of this beautiful little girl. She lives in the control tower. She looks with the binoculars and has a look and see what's going on at every single gate of the airport. So remember this big airport. We have the control tower right over there. That's where she's situated. She has binoculars. She looks at all these gates and has to figure out which state of the turnaround process is in. As you can imagine, that doesn't really scale very well, right? So it's something we need to fix. So the thing that Schiphol came up with is basically very simple. Let's just put cameras on the aircraft in front of the gate. So we can monitor everything that's happening while the aircraft is docked at the gate. So what we want from those camera images is basically, so we'll take a stream of images, a camera feed, we need to apply some magic that we have to build. And we need to end up with events. Right? We need to know, for example, when does fueling start? When does fueling end? If you know when fueling starts, you probably can predict when fueling will end. If you know that you're in some sort of state in the turnaround and fueling hasn't started yet, you could potentially act on that as an airport. So we actually like to focus on this part. This magic system that we built is actually capable of spitting out all these events. So this is our magic system. We do everything streaming. So we stream in the images, cameras, multiple gates, multiple cameras per aircraft. And the first thing we do is basically a unification. So what it means, we'll have 2 images per gate, and we need to unify it into one data point in time. Why it is important? We'll get to that later. After that, we do some object detection. So we'll try to see which kinds of objects are in this data point. Like, is there an aircraft? Maybe is there a high loader? Is there a catering truck? And the last part is, once we have the objects, we could potentially generate these events. So, why do we need this? So these are 2 captures of what the cameras see. And as you might notice, the timestamps, they're pretty close, but they don't add up. They don't match. Both of these images depict one particular state of the turnaround for that timestamp. As you can see, there's this really small staircase here, which is an important object, that you can't really see on the left side. So you kind of need both images to tell the whole state of your turnaround. And the timestamps don't add up. Other than that, there's also no ID. There's no foreign key that we can join on. The cameras are not synced up. So we need a way to tell that these images who come in the stream are basically from the same timestamp. What could also happen, that one of the cameras drops out and we only get one image. Either left or right. Maybe both images drop. Maybe there's rain on the cameras, which means one of the images is pretty much useless. So we need to take care of that. And the first thing we built is basically a way of unifying these camera images into one data point in time. So we built everything in Python, mainly because we work with data scientists. Data scientists kind of like Python. So it would be easy for us to basically map that to some sort of Docker image, having a Python code, putting that in Kubernetes and running it. So let's say an image arrives at timestamp 0. All good? We have another image arriving at timestamp 1. Then the matching algorithm actually takes care, it looks at both, and it figures out that, okay, these are close enough, this is a match, I will combine them, and I will ship them off. So, let's say a timestamp 3 arrives. There will not be an image for the other camera. Happens, right? Then we have a timestamp 6 that arrives. And then suddenly we have a timestamp 8. So as you can imagine, we have to queue a bit. So in our streaming engine, we have to queue these images for a while. And the longer you make the queue, the more accurate your matching will be, but also the more delay you will add into your stream. And this is kind of a trade-off, right? Because you want to act upon your events as quick as possible. If you're 10 minutes late, maybe it's pointless. So there's a lot of playing around with correct parameters. Since there's no match for timestamp 3, we'll just take timestamp 3 because it's still valuable information, and we just ship it off to the next step. Timestamp 6 moves forward in the queue. We figure out that it's a match, and we ship them off. So this is basically what's happening in the unification of the images, which is a very important part of a process. So for the next part, I'll hand it over to my esteemed colleague Daniel, who will talk about object detection and event generation.
Yes, thank you very much, Tim. So quick heads up, quick disclaimer. I'm not a data scientist, so we're not going to be diving deep into how this TensorFlow model works. We are going to be looking at what is it exactly, what's it doing, but we won't actually be doing like a deep dive. Our colleagues, our data scientist colleagues, have done talks in the past about this, but that's not the focus of our talk today. So object detection. What does this actually look like just to show a real turnaround? What we would have seen if the video would have worked is basically a full turnaround. In this case, it was a KLM jet, which is the Dutch national carrier. So a lot of KLM happens at Schiphol. You can see a couple of things down there on the bottom, and the idea is that a Gantt chart will kind of get generated. So as objects start appearing in this view, you'll actually start generating these beautiful bars that will show up, and then you can actually see, so how long was the GPU in place, which is like a power unit that they need while they're stationary, because they can't obviously have their jet engines on permanently while they're parked. And the same applies for things like high loaders, lavatory trucks, all of those things. What you will also notice, and that's why it's a bit sad that we can't see the video, is that a lot of these things, so some things happen once, like say refueling we'd expect to happen once, but some things like cargo doors opening can happen multiple times. And some of these things could actually be red flags, like if refueling happens 5 times, then probably that's telling air traffic control, hey, we might have some technical glitch on this aircraft. This might give us some trouble. Luckily, we do have this overview of some of the objects and events that we can recognize. So I'm not going to go through each and every one of them, but this is just to show you how much actually goes on while you're sitting queuing up at security, waiting at the gate to get on your aircraft. All of these things happen, and all of them are arranged by the airline. It will also differ per airline how exactly these processes work, but it will also differ where the plane is going, how large the plane is, all that kind of stuff. How many vegetarians maybe were on board, whether the catering truck needs to come twice, maybe some special meals, that kind of stuff. So there's a lot of variation, and basically the airport knows nothing. So the beautiful video that we didn't see was all generated on batch. So we started off just gathering a lot of data from these cameras that were there and just saying, okay, data scientists, go do something with this data. It looks awesome. As our esteemed colleague from GoDataDriven always tells us, batches are for barbecues. We want to do streaming. So this is kind of how we approached getting a TensorFlow model into a streaming environment, which for us was something new we'd never really done before. And we also needed to sort of experiment and find our feet in how we actually how to do this. So we actually took a very iterative approach. Our initial trial run was trying to run TensorFlow on top of Databricks. So at Schiphol, we actually used Databricks quite extensively. It was easy, the infrastructure was there. Databricks has an ML runtime that works quite nicely. You get a lot of packages pre-installed. And the end result was, it worked. It wasn't pretty. It did kind of work though. We could hook up Spark to Kafka and then stream in from Spark into TensorFlow, do the magic that our data scientists were doing, output the results. The one thing we didn't really like about this though is that it kind of felt like a square peg in a round hole. Like we were using Spark because we had to on Databricks, but we weren't actually using Spark because Spark. So we sort of said, okay, maybe this isn't the right tool. So let's try something else. So our second iteration was, okay, maybe if we switch to Kubernetes, we can run things in Docker and in that way achieve our scaling. Spark obviously is great for scaling up on larger data sets. And that's something we figured we knew we would want because at Schiphol there are about 100 gates. So if you had to process images every couple of seconds from every gate, you need a lot of compute and you need to be able to scale up quickly. So our second iteration was trying TensorFlow serving. So who here has used TensorFlow serving? Awesome, one guy, awesome. So please correct me if I'm wrong about this, but TensorFlow serving is a really easy way to spin up an API for your trained TensorFlow model. So you can basically take your frozen TensorFlow graph, put it in your Docker image, and you'll get a REST API and a gRPC API for free. So it's super, super easy. And this was actually where we were for quite a long time. We were quite happy. The biggest downside that we found is that obviously it being a REST/gRPC API, you had to have some component making the calls. All of our messages, all of our images are sent on a Kafka bus. So actually the interface between Kafka and TensorFlow serving is a bit awkward. We managed to work around it, but it wasn't ideal. And that sort of led us to iteration 3, where we're at now, is basically dropping TensorFlow serving and just hooking Kafka up directly into TensorFlow. This also was a bit of a hack around. We had to mess around with all sorts of code and stuff that we had to figure out. The really nice thing about this is the simplification that we got of our setup. We lost a bunch of components. We didn't have to interact with this API anymore. And we also gained quite a lot of speed. And I'm going to get to that right now. Because anybody here that has ever worked with deep learning or TensorFlow or anything like that knows there's always this blue pill, red pill decision moment. Where the blue pill and the red pill are, we're going to say Intel and NVIDIA in this case. Please insert your CPU or GPU manufacturer if you don't like these ones. These were the two options we had running on the cloud that we're running on. So our data scientists said, yeah, we need GPUs, we need GPUs. Schiphol actually bought a really beefy physical desktop machine that sat under the desk with four massive GPUs, which was awesome in the winter because it kept us nice and cozy. In the summer, it got a bit hot. When it was like 40 degrees Celsius outside, and then we had this thing with them training models. We actually had a model freeze. We wouldn't let them train models in the summer because it just wasn't nice to sit there anymore. So us being data engineers and not knowing too much about the internals of these deep learning models, took our data scientists' word and like, okay, we need GPUs. We'll see if we can get that to work. And we did get it to work. But we also kept an eye on what the CPU performance would actually be like, just to make sure that we were keeping our options open if we would need to. And the results look something like this. So, as I said, we worked in a very iterative way. Iteration 1 was okay, it worked, but I mean, that was pretty much the only upside. Iteration 2 was already a lot better because it reduced our components, it was a better fit for the problem. And iteration 3 simplified our setup, but also sped us up. So you'll notice in iteration 1, there's no difference between GPU and CPU. That's because we actually didn't manage to get the GPU support working correctly for some reason. We tried, but we couldn't get it to work. By the time we got to iteration 2, you can see that GPU is really starting to outperform CPU. Iteration 3 is the same. You'll notice that there is no y-axis here. We did that on purpose because we don't want you to think that these are in any way scientifically validated numbers. This was us just running a script, using some timing stuff, and then seeing what would happen. Your mileage may vary depending on your machines, on how large the images are, what kind of model you're using. This was just roughly our experience. The nice thing about ending up in this place was that, as you all know, GPUs are loved by all data scientists, but not loved that much by the person that pays the bill. So one GPU on our cloud would cost us 800 euros or dollars a month. For the scale that we were looking at, we were going to need quite a few of these. So it was starting to get to the stage where we're like, these things are pretty pricey. So by the time we got to iteration 3, the nice thing was that we got our speed on the CPU down to a level where we went back to the business and said, hey, look, this is where we're at. We have a GPU, which is a factor 10 quicker, roughly. We also have a CPU, which is slower, but is also much cheaper. What do you want? And so the thing that we took away from this is we made a technical problem, to use Intel or NVIDIA, to use GPUs or CPUs, a business problem. We basically say, well, it's up to you. We can change the one letter from GPU to CPU, and it's not my problem. Just be aware that this is the trade-off. You're trading speed for money, money for speed. Depends on your use case. If we move on to the final part of our pipeline, we are looking at event generation. So this is where we're in a state where we've detected these objects. We've detected these fuel trucks, high loaders, maybe the passenger, what do you call them? The passenger bridges that we all walk in into the aircraft over. So the first time I was talking to our data scientists, I didn't quite understand why we would need this, right? I mean, we've detected the object, so we're good. Well, it's a bit more nuanced than that, because what object detection will do is we'll output this, right? It will say, okay, I see an aircraft, and this is the timestamp. It will do this every 5 seconds, though. So if you give this to your analysts, they'll go crazy. They'll just be like, yeah, what am I doing with all this white noise? I'm going to sit looking at this kind of message for 2 hours while the plane is being turned around. Yeah, the aircraft is there, I get it. You don't need to keep telling me. So that's where event generation came in and why we actually need this. So to give you a bit of an example, now I should say before we start, this is a bit of a hypothetical because we work slightly differently than this. So let's say this aircraft arrives. Okay, awesome. So on the right down there, you'll see this aircraft present and aircraft absent, the two states that an aircraft can be in, right? It's either there or it's not there. So you'll notice we're sliding this blue box. Let's have a look if I can actually use this. We're sliding this blue box over this timeline, which is the x-axis. So the reason we're doing that is we cannot depend on a single observation from the object detection model to actually trigger an event. This was also a requirement from the business. They didn't want any jitters in the object detection model giving them sort of white noise. The reasons for white noise can be really diverse. So if any of you have ever been to the Netherlands, you know it's quite windy. So the cameras also move slightly when they're up on their stands. We also see sometimes that aircraft are driving past in the background. It's just taxiing to their ramp, so that could actually confuse the model a bit. And finally, and that's the example that Tim just gave, in some cases we also might just not have an image. We might just be missing one of the cameras. So we need to make sure that what we're seeing or the things that we've seen actually are sufficient to generate an event. So hence the window. So in this case, the aircraft is clearly there. We've also seen, in this case, we actually have seen the aircraft, but it's not quite enough to generate an event yet. We're just going to hold on for a few more seconds. So let's continue. The aircraft keeps on moving. Now it's firmly within the window. We can see the window is now it's just completely filled with this airplane. So we say, okay, aircraft arrives, this is the time, this is the ramp, and this is the airport. In our case, it's quite obvious what the airport is going to be. And we do exactly the same at the other end. So the aircraft gets turned around, all of these processes happen in between. And we actually wait until the aircraft is fully out of the window, is actually completely gone from the ramp, from the gate, before generating this aircraft departs. Please note that these are hypothetical events. They're not actual names of the events, but this is the easiest example to give without having to go into too much technical detail about how aircraft turnarounds work. So in terms of how event generation works, we call them business rules because they're sort of defined by the business, but not really. So we sort of had to figure out what an actual aircraft departs event would mean or what a fuel truck departs would mean. So this is some pseudocode from one of our events. So I'm going to walk you through it really quickly. So if we look at the very top, we're trying to see, should I generate an event fuel truck arrives? First step we do is if the fuel truck is already there, that means we've generated the event before, or the aircraft isn't there, we just return immediately. Don't care. If the fuel truck parks up at a gate for whatever reason, but there's no plane, it's not a turnaround, not interested. Next step is super simple. What we actually just start to do is count the number of trucks that we see in our view. And at the end, we just say, okay, well, what's the ratio? And how many of the images do we actually see the fuel truck? And this is also to sort of counteract the effect of maybe missing a camera image for whatever reason. Maybe the network was flaky, maybe the camera just blew out, whatever. Then we just say, well, if it's present for more than whatever we configured it to be, we'll say, okay, the fuel truck must be there. As I said, this is a super simplified version of what we actually do. We have events that are much more complicated, but you kind of get the idea. We sort of need to figure out, okay, based on the images, based on these detections, is it there? Should we actually trigger an event? So we've slain quite a few dragons along the way. I think the biggest one was actually getting TensorFlow to run with Kafka. It was the biggest challenge, but also the one that in the end probably was the most rewarding one. But we do have some other dragons that we still need to slay. So if you guys have input on this, more than welcome. We're very open to it. So the three topics we really still are thinking about is model management. How are we actually going to take this TensorFlow model, which consists of this frozen graph and a label map, and make sure that we can upgrade, that we can roll back if stuff is bad, monitor its performance. So right now we're thinking of using MLflow with the new registry. But if you have other ideas, or if you have bad or good experiences with MLflow, please let us know. Another thing is that in our diagram, you can already see we have quite a few components. So these are all microservices in a sense, and we're passing messages in between. So upgrading microservices can be a bit awkward sometimes, especially making it graceful, and especially when you start doing schema evolution or start changing your schema. So we're thinking in the lines of Avro, doing something like that. Again, open to suggestions. And the final one, which is going to be the most interesting one, I would say, is right now we're doing this at Amsterdam Schiphol Airport. There are some plans to start doing this at other airports within the group. And then you start thinking of how we're actually going to scale this out from one physical location to multiple. Do we need to set up several instances of the same thing? Do we use one instance? Do we use edge computing? I don't know. We're still sort of open on that. But it's something we need to start thinking about. We do also have some general advice, things that we learned the hard way in some cases, sometimes the less hard way, that we just sort of would like to give to you as some takeaways. So the first thing is script everything. Sometimes it seems like a big investment to make, and it's like, oh, this is going to take us a week to build up this Ansible playbook to reconstruct things. It's worth it. Every time we built something like this, we were like, we should have done this sooner. So the biggest anecdotal war story here is that we had a massive outage of our Kubernetes cluster, which basically completely bricked the entire cluster. And it took us like 2 days to fully recover. The learning point for us was like, okay, we need to be able to do this quicker. We don't want to have all these manual actions, all these things. So we built an Ansible playbook, and now we can do it in half an hour. And that's sort of the way we try to operate, at least. The second one is that it's really important to iterate. So we could have just gone down the rabbit hole completely on the Databricks and TensorFlow solution that we had at the very start. We probably would have got it to work, but at some point we also just had to say, okay, it's okay for now. You know, this is like pre-alpha version, we're good, let's just accept it. You don't need to build the sports car on day one. Build the skateboard, be happy with the skateboard, enjoy the skateboard. We're probably not even at the sports car yet. We're probably on the bicycle somewhere. We're happy with the bicycle. But if you have ideas on how to get us onto the motorbike, let us know. Get people in the same boat and get them rowing in the same direction. So this is the whole GPU, CPU discussion that we were having internally as a team, and we found it super valuable once we could actually bring this to the business and get them involved, because they have valuable insight, but in the end they're also going to be the people who are using it. So we can be using like technology and run up huge costs to get sub-second latency, but if they don't care, what's the point? It should be their decision in the end. Use the right tool for the right job. If you have a screw and you need to hang up a painting in your house, you can get the screw into your wall with your hammer. It's probably not the best solution. It will work. Just try to always be critical of the tools you're using. Try to think, should I really be doing this? Is this really the way to go? So with that, that's some of our general advice. We do have office hours after the break, I think, because that's in like 10, 15 minutes. Please, if you have any more questions or are interested in hearing more or maybe have advice, some tips, whatever, come and see us. If there are questions that we cannot answer as engineers, our product owner, Afka, that's her email address up there. So you can also reach out to her just in case you want to know more about the project or how we're going to be doing this. So thank you very much.
Thank you.
I know you said it was kind of an iterative process. I'm curious kind of what the elapsed time was for initiation of project and kind of to get to a couple of those phases.
Sure. Yeah, so the video that we initially showed, that we didn't show, unfortunately, our data scientists had a experiment week and they built that in a week. So that was just a basic idea, like, can we even do this with deep learning, with object detection? In terms of actually getting this pipeline into production, I think we started in roughly January, February was when we really started scaling up the team. And now we're in a state where we're outputting live events for a ramp, for a gate.
Hi, thanks for your talk. That was great. How did you manage, or how do you manage your Kubernetes? Is it cloud-based, or as you mentioned, do you have it scripted with Ansible or some other tools? I know, like Kops or something like that.
So both, actually. So it's cloud-based, but we're the kind of engineers that anytime you click the mouse, we get annoyed. So we said, okay, we need to be able to do the scripting. So actually, with our Ansible playbook, we spin up Kubernetes cluster or clusters in the cloud. And what we actually do is provision the whole thing. So storage, credentials, everything.
Can you repeat What's the difference between the second and third iteration? You just removed serving out of the equation?
Yeah, so so the question is just for the recording about what the difference is between serving and not serving. So serving is just this super simple layer that allows us to expose a REST API or gRPC API, if that's what you like. So the biggest difference is that you don't need a separate service that calls this API, that consumes a message from Kafka and then calls the API, waits for a response, gets the response, puts it back on Kafka. So instead of that, we just stripped away that layer and we just said, okay, let's just take this plug and just plug it straight in, where we just actually get the message and just feed it straight into the TensorFlow model. So for us, it was a bit of unknown territory because we weren't that familiar with TensorFlow. But it led to a massive speed up. And it also led to a whole simplification of our setup in that we could lose a component. We didn't need this thing calling TensorFlow serving anymore. So all in all, TensorFlow serving is really nice. It's really awesome to quickly get something running. And I'm sure there are ways of making it quicker than what we were doing, but for us, this was a nice iteration.
Yeah, thanks for the talk. That was actually pretty fun to go through. But I'm curious, did this actually make a difference, like regarding like being able to, generate events and report that to the
it's a really good question. It's also something that for us right now is still a bit hard to tell. So we've been told that having this information and having it reliably it could dramatically reduce delays. Mostly because in some cases, the example that Tim mentioned about fuel truck not being there, have no fuel in the aircraft 10 minutes before departure, that's not something generally now that the airport even knows. So what happens now is when an aircraft wants to leave, the pilot says, hey, tower, I'd like to leave. But until they get that call, they have no idea. After a while, after it's missed its target departure time, they might say, hey, guys, what's up? Are you okay? I don't really have an answer for you on that one, how much it's going to make a difference. We hope a lot.
Hey, so quick question. On the end of your pipeline, it seems like you're generating events and they're coming off, going somewhere. Do you have another part of the pipeline that aggregates these for analytics later as well, or is this mainly just a place this goes off and people can look at it in real time to determine what's going on?
Yeah, so we actually have a few, so we're a data provider basically, and we have a few consumers that consume our data, and one of them is analytics. So we actually sync our data into Databricks, so the analysts can have a look at how well the events are and how they compare to the real-life data, for as far as it's possible. And we have a consumer that actually tries to make this Gantt chart that we try to show, which monitors the actual live turnaround. So yeah, we have multiple consumers of the data.
So it's actually a great teaser for the office hours. If you come to the office hours, we'll make sure you can see the video if you really want to see it.
So one more question, adding to the Kafka question before. Did you monitor how the objects are queued, or if you have fast enough TensorFlow worker, and if it's not gonna fail you because of too much data at the same time?
Yeah, so actually the prediction, so the inference of the objects is faster than the rate at which the images arrive. So for now, we're good. So we do keep monitoring everything that's happening in our system, how long it takes, how much resources they take. The moment that we feel like we're hitting the max of our infrastructure, we need to scale.